The second angle we need to determine is the angle Y. Consider this triangle CBA. We get the angles Y by using the first getting the length of C to A, which is using this angle, by using this length 364 millimeters, and using the cosine law, we get the angle Y is about 87.5 degree. Therefore, the psi angle is 180 degree minus x plus y. X is here, and y is here. 180 of minus this angle is the psi angle. The next angle we will need to determine is the phi angle. We can use the loop vector equation. Arctan of this equation, we get the phi angle is 17.22 degree. Now all the angles we need to use is completed. The theta angle is 90 degree, the psi angle is 83.04 degree, and the phi angle is 17.22 degree. We'll now use the position loop equation. The position A plus this equation basically means the B position of point B equals the position point B. But we'll determine it using two perspective. A plus B minus A, the position A plus B minus A, which is this length, which is meaning then that position A plus B minus A, which is position B, equals to C plus B minus C. Position C from here to here, C plus B minus C. Here plus here is the same as B. We will derivating this to obtain the velocity loop equation because the velocity is a derivative of the position. We'll determine the vector of point A, point B minus A, point C, and point B minus C, which is this equation. And derivating it, we will get this equation. Now, because we only need to determine the psi dot angle, psi dot, we will need to eliminate the phi dot part, because it will means that if we not eliminate this part, there will be two unknown with only one equation. We'll use the dot product. That means if we cos phi times cos phi is cos quadrat phi, and sin phi times cos phi is sin square phi. That will eliminate each other, and this term like here will eliminate it from the equation. The next term we will to get is the psi dot term. We'll just need to simplify this term like here to this term using the trigonometry law. Sin cos minus sin theta cos phi plus cos theta sinus phi is the same as sinus of phi minus theta, and the same as this term like here, sinus of phi minus psi times theta dot. Theta dot is we get the theta dot from the problem, which is 120 RPM, but we'll change it to the radian per second. We need to type one rotation is the same as 2 phi, but per minute we need to change the minute to term to the second term, which is 60 seconds, and the theta dot is the same as 12.6 radian per second. We'll need to plug in all the numbers to this equation and get the final angular velocity of the crashing ram is 4.4 radian per second. I think that's about it, ma'am.
All right, thank you. That's very good. Is there any questions? So there's no feedback from others. One thing, well, all of this looks perfect, but then I realized one thing. So if you go up a little bit to your elimination, yes, this one. So you derive vector A, or A cos
Yes.
theta, this is correct. B minus A, this is correct. Vector C and vector BC, this is also correct. And then you derived it with respect to time. Only small mistake there. Theta dot plus AB, is it cos or sine? Because both are cos sine.
Oh yeah, I'm sorry. I think it's me. I don't get what is your question, ma'am. Can you please repeat it again?
If you take a look at it carefully, derivating this, we will get velocity loop equation, right? Minus OA sine theta, OA cos theta, theta dot plus minus AB cos P and AB cos P. Both are cos sine.
Oh yes, I think that's the problem. But I think the last about the final number is doesn't get changed because this term right here will be 0 in the next term because we'll eliminate this theta dot part using the dot product.
This is what I mean.
Yes,
You have
that's the problem right
minus
here.
AB cos
Yes.
minus AB cos P and AB cos P. This is not correct.
This was supposed to be sinus.
Right.
Sinus.
Okay.
I think that's my mistake.
Yeah, that's a small mistake, but just have to be careful. Zero. All right, I think this is clear to me. Is there any questions? One thing, just one thing. Can you go down again? What is the final results of?
I think I get it about 4.4 radian per second.
4.4. Okay, 4.4 radian per second. Okay, thank you very much, Farhan. You can now stop sharing.
Okay, thank you, man.
All right, so is there anyone who wants to try? I think the next questions. How many questions were there? There were 2 questions, I guess. Is there anyone who wants to try? It's better for you to try it by yourself because in the exam, I will only ask you to solve the problem by using the vector loop equations. For finding angle, you can use trigonometry equations and any other geometry approach. But for finding the velocities and accelerations, you need to derive the vector loop equations. Okay, so if there's no one, will you excuse me for a moment? All right, so let me now continue to the next topic. We are now in the week 11. So in the week 12, hopefully, maybe not next week, the week after, we will have um, a quiz for this, finding the positions, velocity, and accelerations. So now we will continue to the next topic about accelerations. So basically, acceleration is the rate of change of velocity. So it means you need to know how to derive velocity first, then you will know how to find the accelerations. So here we see the roller coaster is going up and down. Initially, it's going up quite slow. Then, when it reaches the top, it's it it's slowing down and it reaches almost zero. Usually, it stops right when you are riding a roller coaster. The carriage will be stopping at the top of the roller coaster. Then it's going down slowly first, then it's going faster when it reaches the bottom, and so on and so on. So now we need to know what is the acceleration. So we want to find the manner. The manner is the behavior in which certain points, so pay attention, certain points. So if we consider a car is a point, like in the first meetings, in the first 3 meetings of our class. So if we consider a car is a point, then we want to find the acceleration of that car as a point. So we want to find or determine the manner in which certain points on the mechanisms are either speeding up or slowing down, just like in the figure. And I believe you know what is the definition of acceleration. And then acceleration, you will have two types, just like in velocity, you have linear and angular acceleration. So in linear acceleration, from the name linear, so it means you just walk in a straight line. Okay, and it defines the rate of change in linear velocity. So if you use this formula, this is actually this is the average acceleration. So it actually doesn't apply to this kind of problem. So in this kind of problem, at every point, the acceleration and velocity are different. So you cannot use this formula basically because this is average acceleration. But this just to show you that we have a linear acceleration, which is a time derivative from the linear velocity. Then we also have angular acceleration. Um, we define it as an alpha. You can define it as a theta double dot. Okay, so alpha here is defined as angular velocity, angular accelerations, defined as a time derivative of Excuse me. So defined as a time derivative of um, angular velocity. Okay, so we have omega. So basically, you can define it either theta dot for omega, or you can define it as a omega. That's also fine. And for alpha is twice derivative, time derivative of angular position. So remember, in kinematics, I always uh, told you this from the very beginning. We have two different terms, kinematics and kinetics. Both define dynamics. So in kinematics, you will deal only with three things: positions, velocity, and accelerations. You can also deal with jerk. Jerk is the third derivative. That's also included in kinematics. All right, now let's take a look here. The first example, finding the acceleration. This is a simple example. So we have a grinding wheel, just like in the right figure. We have a grinding wheel like this. It is rotating with velocity omega and accelerations of alpha. And then the grinding wheel will speed up to 1800 RPM in 2 seconds. Okay, when the motor is turned on, assuming that it should be turned on when the motor is turned on, assuming that the speed up is at constant rate, find number one, angular acceleration, and number two, angular displacement from initial. So you have two different things here. The first one is accelerations, angular acceleration. We know that it has 1800 RPM is the velocity after 2 seconds. And then we want to find what is the distance. Here we call it as the angular displacement from initial. In this case, the problem is the rate of change is constant, because initially the grinding wheel is at rest position. It stops. It stops like this, and in the final acceleration, in the final position, it has velocity 1800 RPM. So RPM is revolution per minute, revolution, okay, not the rotations. So we call it revolution per minute. So one revolution is 2 pi, you know it, because it is one circle. So you need to find it in radian. Okay, so everything calculated usually will be in radian per second for either for velocity or for accelerations. So we have this radian per second, and we know it because this is constant, because the acceleration is constant. So we can just simply finding the final velocity minus the initial velocity divided by the durations, 2 seconds. So we have this constant acceleration. Okay, so this is not always the case. In the mechanisms, just like in the roller coaster, you will reach the top with minimum velocity, and then you go down with maximum velocity. So it goes up and down with different velocity. Then it means you don't have a constant acceleration. Then next, what is the displacement, the total displacement. Okay, so finding the total displacement, if you see this formula, this is like in our first meetings for particle and rigid bodies. This applies only for constant velocity, again, constant accelerations. Right, so we can apply this. We have the omega initial, so basically we have the displacement due to the initial velocity. The initial is 0 because the grinding wheel was at rest. And then we have this due to the constant accelerations. Now let's move on to the accelerations of general points. Suppose we have a point A. Please take a look at the figure in the right. I will tell you later on. Okay, so we have a point, any point in the rigid body. So let's say if this point is moving like this, so this is basically from the previous meetings of our class. So if A is moving in this path, right, you know that it will have a velocity. Linear velocity is always tangent to the curve. Okay, tangent to the curve exactly at that point, right? So suppose that this point is now in this position. So what is VA? VA is no longer like this. Okay, so VA will be to another direction. Okay, and then you know that A will have a linear velocity or tangent. Velocity is always tangent to this direction with VA. It doesn't have normal velocity. It doesn't exist, but it has acceleration both in tangent direction and in normal direction. So we have it in the normal direction and also in tangent direction. Right, so the magnitude of velocity, now we have two ways in defining this. The first one, magnitude of velocity changes. Right, so it produces acceleration along the path. Okay, so VA, the value of VA always change. So this is not the case of constant velocity. Okay, so the value of VA always change so that it will produce the change of tangential acceleration. Okay, and then next one, the direction of velocity changes. So when you change the direction like this along the path, so it produces centrifugal acceleration perpendicular to the path, which we call it as a normal acceleration. So I remember some students, I'm not sure whether here or in another class, they used to call it as a centrifugal force, which is true. So one force, it might have different names. We might call it force in the tangent direction, so we call it tangential force. Or that student, he call it as a centrifugal force, which is also fine. Okay, so we have these two. So now you know that the change in the value, it produces the acceleration along tangential direction. And the change of path, because it changes the path, you will have a normal accelerations. Okay. Now let's take a look the simplest mechanisms. So basically, you have this during the remedial. And by the way, I forgot to tell you when I gave you the remedial about a pendulum. You remember? So you have a box and a pendulum hanging on the pendulum. So that question is actually I gave it to the class, to another class, which is dynamic system and control. You will get that class once you finish this class. You will take that class, dynamic system and control. So it means you have to know how to define dynamics and kinematics first, then you will learn how to derive the control system, which you will learn in the next class. So what I wanted to tell you is the questions in your remedial is actually also in the quiz of the class dynamic system and control. Okay, next we will learn this. This is the simplest mechanisms. This is not even a mechanisms. This is just a simple a bar from point A to point P. Okay, and here we have a pivot. We have a pin or anything which can rotate. Then the displacement is defined by theta. Always remember that when you draw the angle, always draw it from the positive x-axis. In this case, the x-axis is in this horizontal direction. Okay, and then it rotates with some alpha acceleration and also with some omega velocity. Then we can derive it based on this alpha, omega, and theta. We can find the acceleration in the tangential directions, also along the normal direction, right? Because remember, the tangential acceleration appears due to the change of linear velocity, okay? And the normal acceleration appears due to the change of the path, the change of direction. And from these two accelerations, tangent and normal, this is what we call it total accelerations or resultant. So both are the same. Find the total accelerations. So it means you have to find the square root of both tangential acceleration and normal accelerations. Okay, in most cases, you probably in the physics, in the class of physics, you also have learned that if the length is p from A to P, so the length is p. So finding the tangential acceleration is simply p times alpha, right? And then finding the normal acceleration is simply p, the length times omega square. Well, this is true for simple thing like this. So imagine you have to also keep in mind that in real life, we don't deal with this kind of mechanisms, okay? This is too simple. Now we are facing industry revolution 4.0 and etc. etc. So this kind of mechanism is too simple. And this formula applies for such arrangement, for such structure. very simple structure. But to deal with more complex structure, so this kind of formula, it doesn't work. You need to find what is the vector, what is the direction, so you will be able to find the accelerations. So uh, that's why I teach you how to use the vector loop equations. So far, is there any questions? So today I will discuss about Forba mechanisms. That's it. And then I will come back to the assignment. I will discuss how to solve the problem for the assignment number 4. But you are very welcome if one of you wants to try to answer the assignment. So let's continue with four-bar mechanisms. In this class, you will face only four-bar mechanisms and slider crank. That's it. That's very basic, actually. That you will have to know how to do it. And here we have a four-bar mechanisms. Again, you saw it from the last meetings. We now want to derive the velocity loop equations. You remember this one, so we find the vector A. Vector A is decomposed into the x component and the y component. You need to understand this, why we have to put it this way, because this 4-bar linkage or 4-bar mechanism is on the plane x and y, so that's why you define it as an x component and y component. So I hope you already understand this, okay? And then AB, vector AB is this, vector C and vector B, CB. Then you derive this equation with respect to time. Then you get this theta dot and phi dot and psi dot. All right, and now you already saw this as well, finding the velocity. Suppose that, I will go back. Okay, suppose that find the velocity of the coupler link. The coupler link means the phi dot. Here is my phi dot. Knowing that the value of the input and the output, find the coupler length, angular velocity. So this is the angular velocity. And then again, here, knowing the value of the input and the input, the phi dot, and the coupler length, the phi dot and theta dot, the input and the coupler length angular velocity. Find the output angular velocity psi dot. So you can do this right from the previous. And now after that, the next question is find the acceleration. What is a theta double dot, for example? What is phi double dot and what is phi psi double dot? So from the previous equation, you derive that again with respect to time. Here is quite tricky. You also have learned the partial derivative, right, from the engineering mathematics 1 and 2. So I will try to write it down here. So here, if you see, this is the component from theta, and this is the component from phi, and this is the component from psi. The previous equations is like this, minus sine theta. Okay, so the previous equation is like this, minus sine theta and then cos theta, right? And here is theta dot. Please again recall the partial derivative. So when you face this kind of problem, when you have to derive it with respect to time, what will you do? You derive this first. Okay, you derive, it's up to you. You want to derive theta dot first or you want to derive theta. So let's derive theta dot. So if you derive theta dot, then it becomes here. So it becomes theta double dot. Then you keep the same form here. A sine theta. Sorry, here we have A. You can put it in the front, which is fine. A sine theta, A cos sine theta. Okay. And then here you derive this. Then if you derive the inside of the bracket, you get this. Sine theta, you derive it, then it becomes positive cos theta. So positive. Then cos theta here, you derive with respect to time, it becomes minus sine theta. So that's why here we have minus. Then you will get 2 theta. Okay. So that's why you put it here as a theta double dot. Right, so here is also the same. This applies for the phi, this applies for psi. And here, if you characterize each vector, then you will know that this is what we call it as a tangential accelerations. This is what we call as a normal accelerations. Okay, so here is simply the length, and here is the angular accelerations. So you can define it as a h time phi double dot. Right. So this is actually the same as before, only that we know the direction. So this is direction actually. So this is the direction. And here is also the same. So we have h here and we have phi dot square. So we can multiply them, h phi dot square. And inside the bracket is the direction. Okay. So everything is the same. It's just that you need to know what is the directions. If you just simply multiply everything, you've done everything in scalar product, so you lose the sense of what is the directions. Is it perpendicular? Is it going inward, the center, and so on? So that's why I want you to derive this in a vector loop. Okay, so for this is the acceleration in tangential direction, and this is in the normal direction. And for this as well, if you go back to the left, the very left, so this is the tangential, and here is the normal. All right, so do you have any questions? So we have this assignment. Do we have the answer? We don't have the answer. Okay. So we have this one assignment. I will give it to you for next meeting on Monday. Um, I will not discuss it. I will stop here and I will go back to the very beginning. I will discuss about assignment for velocity. Here we have a 4-bar linkage. The mechanism shown in the right is used in distribution center to push boxes along a platform. The input link is driven by an electric motor with angular velocity 25 radian per second, and it accelerates at a rate 500 radian per second square. Okay, find number 1, the instantaneous acceleration at the end of the input link. At the end of the input link, okay. So instantaneous, it means acceleration only at this position, at this instant. Okay, we call it at this instant. So that's why the name is instantaneous. This is what I told you. We cannot use the average velocity equations because at different instant it has different velocity, what we call as an instantaneous. Right, question number 2, find the angular accelerations of coupler and rocker. So we have the input link here, and this is very easy because the length for the input link is the same as the output link. So both lengths are the same. And here the coupler link also has the same length as the ground. And by the way, do you know why we call it as a 4-bar, but actually we have only 3 links? Because you always have to count the ground as well as the link. So the ground is link number 1, here is link number 2, link number 3, and link number 4. Okay. Right, so this is quite simple. So if you have the same length of the input and the output, it means what? It means any velocity of the input link will be the same as the output link. That's a very easy thing to deduce. And another thing is, let me check here whether we have. I think it's already answered. I'm not sure. Okay, let's see this. I will discuss it for you. Let's see here first. Draw the kinematic diagram. That's the simplest thing to do. Number 1, find the instantaneous acceleration at the end of the input link at point A. So it means at point A. Here, you need to find what is the velocity, and the accelerations at the end of the input link. So it means you need to find both the normal and the tangential. You know the omega, the velocity 25, and you know the accelerations 500 radian per second square. And the angle at this instant is 40 degree. So find the accelerations. So if we call it as an instantaneous, so it means find the resultant. First, put the coordinate like this. You know the coordinate at x and at y. You find it. You draw it, the direction of x and y, and then you draw the normal directions and the tangential direction. So the tangential direction will be pointing to this direction because you know the acceleration is clockwise, and so the velocity also clockwise. And how about the coupler link and the output link? So the coupler link will be having the direction like this as well for the phi double dot, and the output link is psi double dot like this. Remember, I told you that because the input and the output, they have the same length of link, so any velocity from the input will be the same for the output, either the angular or the linear, both accelerations and velocity. Okay, so these are the steps for you to find from the angle, and then finding the velocity, and then finally finding the acceleration. Actually, from here we can solve it very easy. Okay, so from here, you know that, yep, so you know here that we have a normal and tangential direction. Um, I want you to define as well the direction, not only the value. Well, from here actually you can simply finding like this, OA times omega square, right? And then A tangential is OA times alpha 2. But now what is the directions? Find what is the directions of this. Um, like this. So I need the directions. So that's why finding by using the vector loop will be very useful. So OA, so you know OA is, let's call it as a L. So L cos theta sine theta. Then you derive with respect to time. So you get VA. Then you have L minus sine theta cos theta, theta dot. Then you have A at point A. You have 2. You have L theta double dot minus, don't forget to put minus, cos theta sine theta plus L theta dot square, dot square, theta double dot minus sine theta cos theta. Okay, and from here you put all the values, so you can get the value of A total, the A total that I drew here, the resultant. This is the resultant, which is from here. Now, next question is what is phi double dot and what is psi double dot? Intuitively, I'm talking to you about the intuitive things. Intuitively, this link is always horizontal. This is for sure. So link AB is always horizontal. Horizontal. Okay. So can you draw the conclusion here? So if AB is always horizontal, so it means there is no phi, there is no change if phi is always 0. right? This is 0. So if you put x here and you put y here, x and y, phi is always 0. 0, so it means phi dot is 0, and then phi double dot is always 0. Okay, this what we call it is a parallelogram. Parallelogram. Okay, because here OA parallel to CB, and then AB parallel to OC. Okay, this is the simplest example because I have discussed it, so I will not give it to you as an assignment. Probably there is no assignment for our next meeting. All right, that's good news for you. There's no assignment for next meeting. We'll come back to the first. We'll come back to the first discussion about the previous assignment. Is there any questions so far?
Yes, I want to ask.
Yes.
You said previously the input and the output velocity is same. Why it is same?
Because it has the same length of link.
Oh, so it's based on the four-bar mechanism.
Yes, this is four-bar mechanism. So in the previous meetings of mechanisms, if you remember, you will have full rotations or not. If you remember that class, if you remember the first meetings of the mechanism delivered by Dr. Tip, if let's say if you have this smaller than this, let's say like this, so here you have probably full rotation and so on. So now what happens if you have the same length? Sorry, I will try it here at the bottom. At the bottom here. So what happens now if you have the same length? Here will be the same as the ground. Here will be the same between the input and the output. So if you have the same length of link, the input and the output, the omega will be the same. So let me call it omega 1 and omega 2. So omega 1 will be the same as omega 2. Alpha 1 will be the same as alpha 2, and so on. Even the theta will be the same. That's of course. Okay, take a look at this picture. The right picture here. You do not measure it. Where is my pen? Okay, my pen is here. You do not measure it from here. This is wrong. Okay, you measure it from the center of rotation. You see, here's the center of rotation. This is a line. In one line, the center of rotation of the output. Okay, then if you draw it upward for both input and output, here's the center of rotation. They are also on the same line. Okay, so that's why the input length, it has the same length, and they are parallel. They are always parallel. Okay, will you excuse me for a moment? Okay, so I hope it's clear. Now let's move on to the previous assignment. Is there any more questions, probably? If not, then I will go back to assignment number 4. Here is, let me open from the classroom. Okay, so I will try to open it from classroom. Here I will discuss, okay, my microphone is on. I will discuss assignment number 4. Assignment number 4. So we have this. Okay, excuse me. It stops in a way. So I will come back here. So the previous file has stopped. So assignment number 4. Please remember that for this class, you will get only 4-ball linkage and slider crank. Those are the simplest mechanisms ever. So by seeing this, you should know, okay, you must know probably. You must know immediately that this is slider crank. Why? Because we have a cylinder, piston and cylinder here. So definitely this is slider crank. Okay, no questions asked. So we have here the slider, or you have seen it as a piston and cylinder up here. So you have this, so this is definitely slider crank. Then you have pin, another pin, and here is another pin. Okay, as it goes up and down, then it can extend it. It can be extended or it can be retracted. Excuse me, sorry. So I should revise once more. So this slider or the piston and cylinder, it can be extended and retracted. Okay, but here is the link here to this. It cannot be extended or retracted. I was wrong before. It can only rotate. Okay, it can only rotate. And let's read here. Heavy roofing materials can be transported on the conveyor to the roof. The conveyor is lifted into place by extending the hydraulic cylinder. At this instant, the cylinder is extending at 8 feet per minute. Find the rate that the conveyor is being lifted. So what is the questions here? The velocity of the conveyor being lifted. We know the cylinder linear velocity, 8 feet per minute, and what else? We know all the dimension, the angle. Now find the rate the conveyor is being lifted. So let's assume that this is the conveyor. This is the conveyor. So find what is the angular velocity, most probably. Draw the kinematic diagrams. This is also tricky, but by practice, you should be able to do it by yourself. And also you have to be very detailed for this. What I mean by detail, point A is not on the same line as point C. You see there is an offset here. Here is point A and here is point C. And the cylinder is along this line, line 2, not line 4. So if you draw it like this, this is definitely wrong. Okay. As I told you, link number 4, it can only rotate. Link number 2, it can rotate and it can translate at the same time. And from here, okay, I will derive it here. So from here, now you derive the equations. Okay, here is 20 degree. Where did you get that? So from previous drawing, it is shown like this, 20 degree. So it is the same for this one. The first step, the first procedure is draw the axis first, draw the frame. So you can either draw it here at point A or you can either draw it here at point C. I would rather draw it at point A. Okay, I would rather draw it at point A. So this is my X, this is my Y. And find the loop vector. So what is the output? The output is at point B. This is my output point. So I can draw the vector as AB is equal to AC plus CB. That's it, only 3. This is simple. And then what is AB? So AB is, what is the angle? The angle is here. Let's call it as a theta. So here is theta. So AB is, let's say this is L or S. So L cos theta sine theta equal to AC. AC is constant. So I might call it ACX and ACY. What is the value? 1 and 3. You can just put it in the value. 1 and 3 plus CB. CB is this. So 160 degree. But I'm not going to put it there. So let's call this CB as a M, probably. So M cos psi, psi. Okay, what is the known again? I forgot. So the cylinder is extending at 8 feet per minute. Find the side dot. Okay, I will write down in the left side in the left side. So L dot is known as 8 feet per, is it per minute? Yeah, per minute. And the question is find the psi dot. What is psi dot? Okay, so now from here, we derive this with respect to time. So we get L dot cos theta sine theta plus we get L theta dot minus sine theta cos theta, right? Remember, this is partial derivative. Why? Because L also changes by time, okay? This point B can be in this position, so L becomes smaller and so on. So that's why you have to derive L first, becomes L dot. Then after that, you derive theta, then it becomes theta dot. Okay, so I'm here at the right side. Now 1 and 3 become 0 and plus m psi dot minus sine psi cos psi. Okay, what do we know? We know only L dot, we don't know this, so we want to eliminate this. We multiplied with cos theta and sine theta. Elimination. And what do you get? So here you eliminate this, you get this L dot cos theta square plus sine square theta, sorry, the square should be put in the middle, equal to what? M psi dot, I will put it down here because it does not, minus sine psi cos theta plus cos psi sine theta. Okay, you know the value, this becomes 1, then so it becomes L dot equal to M psi dot. No, what is this? This is probably is it sine or cosine? I think this is sine. Sine psi minus theta. Please do correct me if I'm wrong. That's it. So you know the value of L dot, I know the value of psi and theta, so I can find psi dot. Okay, so this is easy. Is there any questions? Okay. Is there any questions? If not, then I will end the class for today. Let's meet again on Monday. We'll continue with accelerations. For the slider crank, then I will give some assignments again for you to try, especially for you who feels, okay, I will emphasize this, for you who feels that you got less marks from the first 2 quizzes. So here I'm sharing the code for today's attendance. Don't forget to input it. Today there are 40, how many? 46, 45 students are attending this class. So is there any questions so far? If no, then let's meet again on Monday. Monday is not a holiday, right? So let's meet again on Monday. We'll continue with accelerations. No assignment for today. Probably Monday I will give you assignment, then discuss it again on Thursday. Right, thank you very much for coming and see you on Monday. Happy weekend, everybody.